Did you know that simply scaling the signals wrong on your oscilloscope can make your measurements orders of magnitude worse? I'm Daniel Bogdanoff, and in today's episode of the Keysight Oscilloscopes Webcast Series, we're going to look at tips and techniques for making the best oscilloscope measurements. We'll look at factors of your test and measurement equipment and how you can maximize those factors to make the most accurate measurements possible. The description below has an agenda with linkable time tags, so if you see an item that looks interesting, you can just click on the time tag next to it, skip right to that point in the video. Also, this series is comprised of a number of live webcasts we've done over the past few months, so if this one isn't quite what you're looking for, go ahead and check out the playlist to see if any of those other webcasts apply to you. And while you're at it, subscribe to the Keysight Oscilloscopes channel so you can stay up to date to the new videos that we have coming out. We have new videos every other week. So without further ado, let's get started.
So, to start things out, we're going to have a few example signals. So we're going to look at a system, and it has a 100 kilohertz clock and a 3 megabit per second data signal. And then later in the day, we're going to look at a power saving measurement and an FSK modulated signal, and look at how we can make some measurements on those types of signals and go from making good measurements to great measurements. So here we have our 100 kilohertz clock signal, and I've pulled it up on channel 1 like we're used to seeing on a scope. And this clock signal, when you're designing a system and you want to put a clock in, usually what you're doing is you're just putting a drop-in clock chip. So here on this system that we're looking at today, I have this 100 kilohertz clock chip, and we don't need to debug it and make sure it's working properly and make sure my voltages are correct. But what we do want to do is we want to go in and measure and validate that this signal is actually performing the way I expect it to. So visually this looks okay. Let's start by making some measurements on this and validate this clock chip in our system. So here I've set up the signal and I've zoomed out pretty far, and I'm making a frequency measurement. And you can see some statistics along the bottom of the screen here. We expect this signal to be 100 kilohertz, and my standard deviation right now is about 1.5 kilohertz of my 100 kilohertz measurement, and I've made that measurement about 1,500 times. Now this is pretty good. I'm getting about 1.5% accuracy on this measurement. But I have to ask myself, is this really what the standard deviation of my clock chip is looking like? Or is there something else going on here? Is there something I can do to make a better measurement here? So instead of making a good measurement, I want to make a great measurement. So what happened is I'm at 2 milliseconds per division here. And you can see that my sample rate, so how fast my ADC is sampling, it's sampling at 100 megasamples a second. Now the maximum sample rate of the scope is 5 gigasamples a second. So something happened here, and we'll talk about why the sample rate's lower. So what I've done here is I've zoomed in to 1.2 microseconds per division. So I've gone in to about 100 times closer, and here I have just one waveform on screen. You can see that I'm at 5 gigasamples a second now, so my sample rate has gone up to the maximum sample rate available. And if you look at my standard deviation, this is where it really gets interesting, is my standard deviation around 100 kilohertz is now only 1.5 hertz. When I was zoomed out and at 2 milliseconds per division, I was at 100 megasamples a second, and I had a standard deviation of 1.5 kilohertz. By zooming in on the signal and scaling that to have just one cycle on screen, I'm now able to get a standard deviation that's 1,000 times better and only 1.5 hertz. So the only thing that's changed here has been my sample rate, my time per division. Let's talk about why we have this difference. You can see here that this is kind of this representation of the signal we're looking at, and this brown box is the window we're looking at on the scope. And we have this equation. This is a key equation for using oscilloscopes. And we have memory depth equals acquisition time times your sample rate. So the memory depth is always going to be fixed in your oscilloscope. Usually you want to use the max memory depth. Keysight scopes always use the maximum memory depth. Then you have that as a constant equals your acquisition time, which is the time that you're looking at the signal, which is also a constant, times your sample rate. So what happens if you have a constant memory depth and a constant acquisition time? The sample rate has to be variable. So as I zoom out, I'm going to have to adjust my sample rate in order to get enough samples to fill that full acquisition time. So you can see here, by zooming out, or by zooming in on the signal, I was able to maximize my sample rate, and I was able to get a much better measurement much better frequency measurement with only 1.5 hertz standard deviation instead of that 1.5 kilohertz standard deviation. And by zooming in, I was able to really characterize this clock chip and make sure it's functioning the way I expect it to. So horizontal scaling is very, very important when you go in to make measurements, especially if you want to make a great measurement. Let's now talk about vertical scaling. So we have vertical scaling, and we talk about bits of resolution. So you can see here, again, I have this 100 kilohertz clock signal, and you can see that my standard deviation vertically for my peak-to-peak measurement, I'm making a peak-to-peak measurement, is 18.1 millivolts. And I'm at 770 millivolts per division. So I'm not zoomed in very far vertically on this. Let's see what happens if I zoom in better vertically and maximize the bits of resolution of my scope. You can see that I've gone to 66 millivolts per division, and my standard deviation has gone from 18.1 millivolts down to 1.22 millivolts. So what this tells me is that by scaling my signal vertically, I'm able to make a great peak-to-peak measurement on my signal. So that 18.1 millivolt standard deviation, that's a pretty good measurement, but we want to be able to make great measurements with our oscilloscopes. So by scaling it vertically, I was able to optimize the bits of resolution, which we'll talk about next, and get a great peak-to-peak measurement. So let's look and talk about what bits of resolution actually means. Here I have an example. I have a 2-bit ADC here on the left. And you can see that I have 4 possible levels. I have this red analog signal. That's what would be the equivalent analog signal coming into my ADC. And then I have this blue digitalized waveform that's coming out of my ADC into my digital oscilloscope. And you can see that with a 2-bit ADC, I have 4 different levels. And I get an okay representation of my signal there. But if you look at this next signal on the right here, I have a 3-bit ADC, and I have the exact same analog waveform going in, but the digital waveform going out is going to be, I'm going to have I'm going to have a lot more levels, 8 levels of quantization that I can use for sampling this analog signal. So what happens then if I only use half of this then? If I have my signal zoomed in vertically and I'm only using about half the screen, I'm really only getting about 4 bits of resolution, even though I'm using a 3-bit ADC here. So our scopes are 8 bits, our samplers are 8 bits. So what happened was when I had my signal only scaled on part of the screen, then my ADC was not using its full bits of resolution for the scope, and that's why my measurement wasn't quite as good as when I was able to zoom in fully vertical on the screen. I get a much better standard deviation, so I know more accurately, more precisely how that clock chip is performing. And I'm also, because I'm using the full 8 bits of resolution of my oscilloscope. Another important thing here to talk about is that the bits of resolution of the scope matter, but you also have to consider the full signal path. So you have to consider where you're probing on your board, what probes you're using, and what sort of attenuation ratios and probing solutions you're using from the source of the signal all the way through the ADC into the scope. So the full signal path matters here. So we talked about how it's important, if you want to make great measurements, you have to scale your signal horizontally and scale your signal vertically. Let's now talk about another sample signal. This is a power saving system. So you can see here on screen, this is a typical power saving device. So I have this sleep state where my device is basically going into a sleep state to save power. I don't want to have anything running. I just want it to be as low power consumption as possible. Then I have this communication phase of my signal, and I'm communicating, and that's going to take up hundreds of milliamps or so. And then I have this housekeeping stage, so I basically have to make sure all my communications were proper and accurate, and then I have to tell the system to go back into a sleep state. And that's usually going to take, on average, tens of milliamps for today's power-saving devices. And then you go back into your sleep state. So we want to make some measurements on the signal. We want to measure the charge. How much power am I actually using? And you can see this is about a 5-second cycle. So here we are. We've zoomed in a little bit on the signal, and this is pretty good. Let's look closer at that lower right, and we can see that something interesting here is happening. and it's pretty low on screen, so our bits of resolution are not going to be optimized when we're looking at this. And ultimately, it's lost in the noise of my signal path and of my scope. So we need to find a fix here. So let's figure out how we can better make a measurement on the signal. So an analogy we use here is we talk about zooming in and zooming out. And we're going to talk about a tool we can use to best make those measurements. So here's a picture of a city, and we want to be able to see the city. So this is equivalent to being able to see the communications on my power-saving device. But we also want to be able to see the zoomed-in, high-sensitivity region and see what's happening right in that city square, so to speak. So we want to see the zoomed-in picture. We also want to see the zoomed-out picture. And what that means is I need a very high dynamic range of my probing and my scope. So one tool you can use to make great measurements on this type of system, we have a high sensitivity, high dynamic range current probe, the N2820A. And basically what you can do with this probe is you can double probe from a single point, and you can look at both a zoomed out version of my signal. So here I have this power saving device, and I'm on channel 1 for that. And you can see I have those big communication spikes, and then I have some housekeeping, and I'm not sure what's going on there we want to see. So we also have the zoomed in view. So you can see we have from this probe, we have 2 different channels that are being used at a single probe point, and we're able to optimize the bits of resolution of the scope by viewing it both with the zoomed out view and the zoomed in view. And the scope does some algorithms to make sure that you get one value, and we can measure the charge and the power used by this power-saving device, both in the big communication phases and in those sleep and housekeeping states. So that's one technique you can use to make a good measurement, or even a great measurement, on this type of system. So that was a power-saving system we talked about. We talked about scaling, how that's important. Once you're able to set up your scope appropriately, we want to talk about how you can make measurements quickly. Remember, we're trying to validate this chip. You don't want to spend all day trying to validate this measurement. You just want to do it quickly, fast, check your box, and move on to the next part of your project. So to talk about making fast measurements, we first have to look at the infrastructure of a digital oscilloscope. So there's 2 main types of digital oscilloscopes out there. There's this traditional architecture where everything is pipelined through an ADC, or through a CPU rather. So you have your analog signal coming in, it goes into the ADC fills your memory, and then you do all of your digital channels, all of your plotting, all of your math and processing, all bottlenecks through that CPU. So the performance of your scope and the speed in which you can make measurements is all contingent upon the power of that CPU. What we've done with the Keysight Infiniium series oscilloscopes is we've gone from this traditional architecture to an ASIC-based architecture. So we can do parallel processing inside of this ASIC that we've designed in-house specifically for these oscilloscopes. So you can see in this block diagram we have the analog signals coming in through the ADC. And then once the signal comes out of the ADC, and it pipes things into memory, but we can also do a lot of processing in parallel with that acquisition. So we can do our serial decoding, our digital signals, our plotting, our math, our FFTs. All of that can be done in parallel in order to decrease the dead time of the scope and increase the speed in which you're able to make measurements. So let's talk about that a little bit more. We have our 100 kilohertz clock chip again, and I've zoomed in pretty far horizontally just so I can look at this rise time of my chip. So you can see I've zoomed in, and I'm making a rise time measurement. And I took this measurement in about the course of 1 minute. And you can see that in that minute, because of the ASIC-based infrastructure, I was able to make 35,000 measurements. I'm also able to get statistics corresponding to that rise time measurement. So you can see here, you can see here that I've made 35,000 measurements in a minute because of that infrastructure. And I've scaled the signal appropriately in order to make a great measurement on this rising edge. So I've zoomed in the signal vertically so that I'm optimizing the bits of resolution of the scope. I have the signal about peaked at the top and about peaked at the bottom. And then I've zoomed in horizontally to a time division that allows me to see what I want to see without having any extra space on screen. So in addition to making fast measurements, we want to talk a little bit about waveform update rate, because that also affects our measurements. And generally, the faster your waveform update rate, the faster you're going to be able to make measurements. So the analogy I like to use to describe what waveform update rate means is the analogy of a digital camera. So your sample rate is analogous, or your bandwidth even, is analogous to the megapixel spec of your digital camera. That's basically how fast your scope is able to sample, and that's how fast your camera, or how precise your camera is able to take pictures, how high of resolution they have. Waveform update rate is more analogous to pictures taken per second. So you can see here we have this drummer's about to hit a cymbal, and we've taken this with a very slow-mo camera. So because the camera is such slow motion, it's able to capture all of the harmonics of this cymbal being hit. So this is analogous to waveform update rate. The faster your waveform update rate, the faster you're going to be able to see these, especially transient type characteristics on your signal. So having a fast waveform update rate not only helps you make fast measurements and lets you, quickly acquire and plot and measure data, it also gives you more insight into how your system's behaving. Because when systems break down, it's not going to be slow, it's going to be fast. And you're going to want to be able to see those transients. So on a scope, here is an example of what this will look like. We have an identical signal on the top and on the bottom. And a scope with a slower waveform update rate is going to capture, and it's going to rearm, and it's going to have this dead time. And during that dead time, there's going to be a definite potential that there are glitches in the system, and you want to see those glitches. With a fast waveform update rate, you're able to decrease the scope's dead time and vastly increase the likelihood that you're able to see those glitches. So let's look at a signal. Here's the 3 megabit data signal that we were talking about at the beginning. It's on my system. And I can see that I have a little bit of a glitch here. And I want to go in and measure this glitch, measure signals around this glitch, and figure out what's really happening here. And maybe from these measurements I can determine some root cause. So when I go to do that, I only care about the glitch signal. I don't care about all these other data bits that are coming in. So we want to figure out, before I can measure this well, I'm going to have to be able to isolate this glitch. So in order to isolate that glitch, I need a trigger. And our scopes and scopes out there have a lot of different triggering capabilities. The one we're going to look at today, just to save time and make this a little bit easier to look at, is a trigger that we have unique to Keysight, and it uses the 12.1-inch capacitive touchscreen we talked about. So instead of trying to measure out and get a rise time trigger or a pulse width trigger or a runt pulse trigger, I'm instead going to use the zone trigger that uses our touchscreen. So all you have to do to isolate the signal is draw a box around where that glitch is and select must intersect. And that's going to allow you to isolate the signal. Once the signal has been isolated, we can now go in and make measurements specifically on this part of the signal, so where this glitch is happening. And we don't have to make measurements on the parts of the data bus that we know are operating properly. So here you can see I've made both a rise time measurement and a peak-to-peak measurement, and I have statistics on those. I can tell how many times I've made that measurement. And once I've done that, I've now been able to refine my measurement and make the measurement that I care about and not the measurement that I don't care about. So triggering is important to making a good measurement on your signal. We're going to talk about another way to maximize your ability to make great measurements. This is a slide we saw earlier. It's memory depth is acquisition time times sample rate. This is important because if I want to make fast measurements and I want to make repeated measurements, this could become a hindrance. So let's look at a technique or a tool you can use to make better measurements, especially on something like that glitch, which is pretty infrequent. So we'll talk about a tool that we have on Keysight oscilloscopes called segmented memory. And essentially what this allows you to do is selectively capture parts of your data bus. So what you do is anytime you trigger, it's going to capture just that amount of signal on screen, and we're not going to care about that dead time between, in this example we have pulses. Instead of wasting my memory depth on that dead time between pulses, I can instead just capture parts of the signal that I care about and then make measurements. So let's look at this glitch we saw on our 3 megabit per second data bus on our system. you can see here that I've captured 1,000 segments of this glitch. I've captured 1,000 instances of this glitch. And it took me about 357 seconds to capture 1,000 times. So this glitch happened 1,000 times in about 357 seconds. And we use segmented memory. So using that formula we looked at, we have a 357-second capture times the 2.5 gigasamples a second that I'm sampling at. That's an equivalent memory depth of 893 gigapoints of memory. No matter how hard you look, you're not going to be able to find a scope that has this much memory. But using segmented memory, we're able to refine our capture, and we're able to capture a memory depth that we would normally have no hope of seeing. So, and then we can make measurements on these statistics. So we can go through 1,000 instances, and you can see in our statistics we've made 1,000 measurements, and we have statistics on all of those, of course. So we were able to combine the difficult trigger that would normally be difficult. We made easy with the zone Infiniscan zone touch trigger. We were able to take 1,000 captures over almost 6 minutes of time and capture what would be the equivalent of almost a terabyte of memory. So we talked about refining measurements using segmented memory and using triggering in order to isolate and look at just the signals you care about. One other thing you can do, another way to refine your measurement, is to use mask testing. So here I've gone to this data signal, and I can see here that I have a glitch, probably an issue in my memory controller, but there's definitely a glitch here. So let's look at how we can make a measurement of this glitch in my system. And we'll talk about mask testing as a way to refine measurements. So setting up a mask is pretty easy. You just capture that ideal waveform. This is what I know it's supposed to look like. And you hit auto mask, and it's going to create that mask. And then we hit run on our scope, and it's going to capture for a while. And then we can see, how prevalent is this glitch? Is it going to cause issues for me in the long run? Is it infrequent enough that I probably wouldn't see it with a slower update rate, but having the faster update rate maybe gives me more insight into the scope, into my signal? Let's take a look at this. So you can see here, I've run this mask test. I started it in the morning. I ran it for about 7.5 hours. So the same signal, 7.5 hours. I wanted to see how frequently this glitch appeared. So you can see 7.5 hours, and I've run 5 billion tests. That's a pretty large number of tests. It took 7.5 hours, and because of my hardware-accelerated mask testing in that ASIC, I don't have to slow down my acquisition rate and my sample rate in order to get this many tests on screen. I can just do the mask test in parallel with the rest of my acquisition and measurements. And then in that 5 billion tests, I can see that I've had almost 9,000 failures. And I can also see, so I had about 9,000 failures in that 7.5 hours. And because of my ASIC-based infrastructure, I'm able to see that either yes, this is going to be a problem for me in my system and on my data bus, or no, I can maybe live with that number of failures on my system. And that's all going to depend upon the parameters of your system and of your design. You can also see there's a 6 sigma score and a failure rate. So about 0.0002% failure rate. That's not too bad, but depending on what system you're designing, this could be acceptable or could be unacceptable. This is a way you can refine how you make measurements. Knowing this information, if you wanted to look into it further, you could then trigger on this glitch and go in and make measurements and isolate and try and find the root cause of what's happening here. So we talked about how to refine your measurements, and all of those measurements we made were scaled appropriately. And we were able to do them quickly because of the ASIC-based infrastructure. Let's now talk about different acquisition modes you can use in order to make great oscilloscope measurements. So our Keysight scopes have 3 acquisition modes that we're going to look at today. We have this normal acquisition mode, which we probably use on a day-to-day basis for our scopes. It just samples at the normal sample rate and plots the information on screen. This is pretty useful for day-to-day debugging. We also have this averaging acquisition mode, and this is a waveform-to-waveform averaging acquisition mode. So we can take multiple captures and average those waveforms together. We'll talk about a good use model for that in a bit. And then we also have this high-resolution acquisition mode, and this is a point-to-point averaging mode. And we'll also talk about that a little further on in the slide set here. So you can see here's my 100 kilohertz clock signal. I'm making peak-to-peak measurements on it, and I want to know what acquisition mode I want to use. So this is in regular acquisition mode. Like we said, the scope samples at the specified sample rate, and this is ideal for day-to-day debugging. I scale the signal appropriately on screen. I can just plug this into my system, make some measurements, and see how my system's behaving. That's the one we mostly use on a day-to-day basis. Averaging acquisition mode is a waveform to waveform averaging mode. So you take multiple captures and average multiple waveforms together over time. What this mode is really good for, or best for using, is for measuring periodic signals, and it also will hide transient noise and hide glitches on my system. So if I'm not debugging my chip and trying to find glitches, and instead I just want to see, this overarching view of what the waveform looks like and what my clock waveform signal looks like, I can use this averaging mode, and I'm not going to have to worry about noise, and I'm not going to have to worry about glitches, and I can make measurements just on the root, core heart of that signal. Something that you wouldn't want to use averaging acquisition mode for would be an aperiodic signal. So, for example, that 3 megabit per second data bus, I don't want to try to average my high bits and my low bits together. I only want to use this averaging mode for a periodic signal. Our next acquisition mode is this high resolution mode. And instead of being a waveform to waveform averaging mode like averaging mode was, this is more of a point-to-point averaging. So what we do is we use a real-time boxcar averaging system, which essentially means we oversample the system, average points together over a certain period of time, and find an ideal point out of those oversampled points. And then we use that point as our data point to plot onto the screen. So what this does is it reduces random noise on my signal. As the scope sees it, it reduces random noise, so I don't have to worry about thermal noise or shot noise or any of that noise that I'm not really concerned about always when making a measurement. And also vertically, this effectively increases my bits of resolution. So you can see my peak-to-peak measurement here. Standard deviation is about 654 microvolts. In normal mode, my standard deviation on that peak-to-peak measurement was 1.2 millivolts. So I get about a 50% lower standard deviation on this clock signal by using high resolution mode. And again, this goes back to bits of resolution like we were talking about. For the frequency measurement, this standard deviation is about 972 millihertz. And if you think back to when we were measuring that 100 kilohertz clock signal in normal mode, we were getting about a standard deviation of 1.5 hertz. So using high resolution mode gives me about a 35% lower standard deviation on my frequency measurement. So high resolution mode can be a very useful tool for making measurements. So again, we looked at normal mode, which is perfect for day-to-day debugging. I still see all the signal, all the noise, nothing gets averaged out. Averaging mode is great for synchronous noise-free measurements. So if I don't care about my random noise and I'm not really looking for glitches or bugs in my system, it's perfect for making measurements there. And then we also talked about this high resolution mode, which helps me optimize my effective number of bits on my scope and helps me make better measurements there. The downside of high resolution mode is that it could hide some of that noise that is really there on your system that you want to see. So another bonus feature we have here is you can use segmented memory and triggering in addition to those acquisition modes. So all of the mask testing, the triggering we talked about, the segmented memory we talked about, all of those work in each of those different acquisition modes. So you can use all those together using our ASIC-based infrastructure without losing waveform update rate. So acquisition modes are a tool we can use, and we can modulate which acquisition mode we use in order to make great measurements. Let's now look at an FSK modulated signal and make some measurements and characterize this one as well. So here we have an FSK signal. And what I want for this signal, what I'm expecting, is it to hop between 3.2 megahertz and about 400 kilohertz. You can see that it's triggering on an I2C command line here. So I have this I2C command that's talking to my controllers and telling when that frequency should jump from 3.2 meg to 400 kilohertz. And then we're even triggering on this I2C command that initiates the transaction. So we're doing a hardware serial trigger here in order to capture what I want to see on my analog waveform. So the measurement challenge that I have here is to be able to accurately measure these two different frequencies independent of each other. Because I can't just turn on a frequency measurement and hope that all my statistics work out right. I'm going to have to massage the scope and utilize some of the other capabilities we have inside of it, do some techniques to really drill down into the measurement that we want to make. So let's talk about gating with a zoom window. So on top, we have this main signal. You can see we can visually see the transition there. And we can also see our little zoom window up at the top here. And then in the bottom half of the screen, we have the window that we're seeing from that zoom window. So we've zoomed in on a portion of the signal, and we're able to see that, yeah, it's definitely a sine wave. Now we want to measure it. So we look at our measurements here, and we can see, yes, it's 3.2 megahertz, which is what I expect, and my peak-to-peak voltage is about 4.9, right around 5 volts. So I'm only looking at this 3.2 megahertz signal here, and I'm able to gate that measurement by the zoom window. So I'm only making the measurement in the zoom window. We can do the same thing for the 400 kilohertz signal. Again, we have the main signal, we have our zoom window, and you can see that the measurement looks the way I expect it to. It's right at 400 kilohertz. My peak-to-peak voltage I see is a little bit higher. So that's one technique you can use to make better measurements and make more specific measurements to see what you want to be able to see, is gating that measurement with a zoom window. We can also gate measurements another way. Some people don't like to use the zoom window. They'd rather have the signal fully on screen. Another thing you can do is you can gate a measurement with cursors. So you can see here I'm in my measurement settings menu. So I've turned on measurements, I've turned on a frequency measurement, and I can massage some settings here to change how I'm making measurements. So instead of gating on the zoom window, I'm now going to go in and gate my measurement just with my cursors. And you can see I have these two cursors on the bottom. I have some cursors here. And I'm going to make a measurement just between those cursors. And as a side note, the cursor movement is another nice time where the capacitive touchscreen of the oscilloscope becomes really handy. So to move my cursors around, instead of having to go into menus and hit buttons and turn knobs in order to get the cursor right where I want it to go, you can just use your touchscreen and drag and drop that cursor exactly and precisely to where you want it to be. So this is a nice little feature that the capacitive touchscreen gives us the capability to do. So let's look at our measurement here, and we can see I'm measuring on that more dense signal on the left, and sure enough, it's 3.2 megahertz, and that measurement's only being made between the cursors there. And of course, we can do the same thing for the 400 kilohertz portion of our signal. You can see I've moved my cursors over using the touchscreen, and I'm now getting a frequency measurement of 400 kilohertz like I expect to see. And of course, you can still get statistics on all of these measurements. We're able to get those statistics in parallel using the ASIC that we have in our scopes. So those gated measurements are pretty nice, especially for signals like an FSK modulated signal or something where you're a little more concerned about how your signal's changing over time, especially in that acquisition. So let's look at some other tools and techniques you can use to make measurements on your system. So here, briefly, I'm going to look, here's our Infiniium X Series oscilloscope family. We're going to look briefly at the real-time eye and jitter analysis capabilities that we have on the 6000X series. You can see the 6000X goes up to 6 gigahertz, so we can see much faster signals. We get 20 gigasamples a second. So here's a signal here, and I can see my main signal up at the top on channel 1. And I want to make a jitter measurement on the signal and know what's going on here. Jitter is especially useful if you're working with serial buses and you want to make sure that you're going to have a low bit error rate. You can use this jitter analysis package to make sure that your system is going to fit into the specs you expect. So we have our signal, and what we're doing is we're making a time interval error measurement, and then we're plotting the trend of that measurement over time. So you can see as time goes on in my signal, I have this sinusoidal trend to my time interval error measurement. And that time interval error measurement is basically how far the signal's edge is away from where I want my ideal edge to be. And if my edges drift too far ahead or behind of that ideal edge, then I'm going to start having issues at my receiver. So I can see I have this sinusoidal trend to my jitter measurement, my time interval error measurement. This implies to me that there's some aggressor signal. And what I could do then is go in and find the frequency of this trend, and that would help me identify what the aggressor signal is. In addition to the sinusoidal trend plot, I also see that there's an outlier. And what this outlier tells me is that in addition to some aggressor signal that I'm seeing is causing the sinusoidal jitter, I can also assume that there's probably something going on with my memory controller that's causing this outlier. And then on the bottom, I have a histogram of my measurement, and I can see that it's basically a probability distribution function of where my edges are lining up. And I can see that since it's not Gaussian, it's not a normal distribution, it's not just random noise then, and I have this bimodal histogram which tells me I definitely have an aggressor signal somewhere in my system causing issues. So by using this jitter analysis package and the time interval error measurement, I was able to then plot the trend of that time interval error measurement and get closer to identifying the root cause of what the problem is on my system. So once you've figured out what's wrong with your system, so in this case we're taking a real-time eye using that same analysis software package, and we're able to see how tall and how wide my eye is. And depending on your system, this eye may or may not be acceptable to you. If the eye gets too small, your receiver is going to start missing bits and misreading bits, and your bit error rate is going to jump. So by using this real-time eye analysis package, I'm able to look at my eye and verify. I can measure height, width, and I can see what's really happening on my system at my receiver and figure out what the problem is. So you can see, here's my real-time eye. I have a histogram down at the bottom, and this looks Gaussian, so there's a normal distribution. That's pretty good. But I also still see this outlier that I saw on my 3 megabit per second data signal. And I can see that I still haven't fixed that problem, but since my histogram is Gaussian, I know that I'm no longer having that sinusoidal aggressor signal. And then, of course, I can make measurements on my histogram. So I have about 1.3 billion hits, and I have all these measurements for my histogram that are associated with that. This is the first time that we've ever had a jitter real-time eye, that anyone's ever had a jitter real-time eye analysis package on an embedded operating system scope. Another tool we can use, and it looks like I may not have a slide for it, is the Infiniium offline tool. And what the Infiniium offline tool is it's a tool that allows me to share measurements across teams. So I can capture measurements on my scope, and I'm going to jump to that here. So here you can see we have this Infiniium offline tool, and I can capture signals on my Infinivision scopes and export it to a PC that runs this Infiniium offline tool. And what this Infiniium offline tool does is it allows me to capture and share measurements across teams. So if I need to let my coworker know that there's a problem and it's probably something that they need to fix, I can just shoot the waveform over to them, and they can load it into Infiniium offline and see exactly what I'm seeing on my scope. You get some enhanced FFT capabilities. So we have FFT capabilities on the Infinivision scopes. The Infiniium offline gives you a lot more enhanced FFT capabilities on your signals. So if you want to take a one-shot capture of a signal and do some advanced FFT analysis on it, maybe run the signal through some filters first, you could do that in Infiniium offline. And that's going to help you make better FFT measurements. We also have some additional protocol capability and analysis, and we do some advanced jitter and separation. And just like our Infinivision scopes, this does automated measurements. So again, let's look at the scope we were using. We were looking at the Infinivision 4000X series oscilloscope, and you can see that we have our four analog channels like we were talking about. It's 5 tools in one. We were using those analog channels. We saw some digital channels when we were looking at the FSK measurement signal, and those we were able to trigger on an I2C bus that was being decoded and trigger and make measurements specifically on those two different frequency portions of the signal. So we also use the serial protocol analysis there. We have an arbitrary waveform generator. You see those BNCs in the lower left of the scope. You get 2 channels of an arbitrary waveform generator. We also have a digital voltmeter. So if instead of making oscilloscope measurements, you wanted to make a quick DVM measurement, you could use one of the analog channels to do that also. The 12.1-inch capacitive touchscreen is pretty nice. We talked about how you can use cursors and move cursors around to make that happen. We also looked at the zone trigger, which made our triggering a lot easier and faster. And then finally, we have 1 million waveforms per second update rate on the scope. And that's what lets us make those very fast, repetitive measurements, mass tests, and segmented memory. And just so you guys are aware, we also have an application bundle for our Infiniium series scopes. And if you buy this one application bundle license, then you save up to 90%, and you enable every software license on the oscilloscope except for the MSO, which is the digital channels, and bandwidth upgrades. So you get all of the protocol decoding, you get some power analysis, you get that jitter and real-time eye analysis we talked about from the 6000X series, you get the WaveGen, the DVM, the mass testing. So that's what I have for you today. Go ahead, Bill. Thank you.
So let us start with the first one. First question, Daniel. When do I know what horizontal scaling I should use?
That's a great question. So you want to optimize your horizontal scaling so that you're maximizing your sample rate. And traditionally, a rule of thumb, especially if you want to make great measurements by scaling horizontally, is you want to get about 1 cycle of your signal on screen. So you can give it maybe a little division or 2 on either side, but you want to maximize 1 cycle of your signal on screen horizontally, and that's going to give you the best measurements.
Okay. Here's what I want to know about. Can you log the measurements over time?
Also an excellent question. You can log measurements over time. We have another another tool that I didn't talk about today. We call it BenchView. And BenchView is a tool that gives you some basic control over the scope remotely. And you can also log measurements pretty much indefinitely using that BenchView Oscilloscope Pro software tool that we didn't talk about today, but it's out there on the website. So yes, you can.
Okay. Why wouldn't I just use high resolution mode all the time?
So high resolution mode is excellent for maximizing your bits of resolution vertically like we talked about. But the downside of it is if you have some random noise that's inherent in your signal, especially at the higher frequencies, you're not going to have the insight you would in normal acquisition mode into that random noise. So high resolution can be very helpful for drilling down and trying to make a more precise measurement, but it's not always going to be the best, most accurate measurement like you would see in normal acquisition mode.
Will a scope with more bits of resolution make better measurements?
So that's a good question. More bits of resolution does not always make better measurements. So we talked a little bit about how the full signal path matters when you go to make measurements. How you're probing and where you're probing, what sort of inherent noise your scope has, what sort of inherent noise your system and your probing solutions have, those all contribute to how good your measurement's going to be. So you have to consider not just the bits of resolution, but also consider the full signal path that you're measuring when you're looking at your measurements and at your signals. And we talked about vertical scaling just to optimize that one part of what makes a measurement great. But bits of resolution is not the end-all for making great measurements. Effective number of bits of your ADC is not the end-all for making great measurements.
Okay. Here's an interesting one. This person wants to sort of take advantage of the software you have built into the scope. They wanted to know if you could actually import CSV files and sort of do offline analysis. Yeah,
so you can there's 2 different things, and I'm not quite sure 100% where the question is leading. We can, one option is you can load a CSV file, you can load a file into the scope and call that maybe a golden waveform or a reference waveform. So you can load that into the scope and use that to compare the live signals you're capturing. You can also load waveform CSVs into the Infiniium offline software and do all of your scope analysis from that Infiniium offline software based on your CSV file.
Okay. Here's a more generic one. How does probing affect my measurements?
So this goes into what we talked about for the bits of resolution and high res mode conversation. Probing affects your signal path. So if you're probing a serial bus right in the middle of the transmission line, it's not going to be as good of a measurement if you were to measure it right at the receiver or the transmitter. The probe itself that you use also injects some noise into your measurement, and it could even put some loading on your system and show you measurements that aren't actually there. So you want to carefully examine the probes that you're using. We talked about that high dynamic range probe where we're able to double probe that signal and get basically double probe it from the same point and see both the big voltage swings and the small voltage swings. You really want to consider your application and the probes that are available to you in order to make a good measurement.
Okay. And where can you get the software for doing some of this?
So the Infiniium offline software is available on the web page. Do a search for Infiniium offline. I don't remember the product number off the top of my head, but it's available there online. And then for application software on the scope is also available online or through your local distributor or Keysight salesperson.
Okay. With segmented memory, can I scroll through and see different segments, and can I also export each of the various pieces?
Yeah. So segmented memory, like we talked about, we looked at the 1,000th instance of that capture. You can go through and you can use the touch screen and just touch whichever segment you want to see. It's going to pull it up on screen. You can export the waveform information. You can export time tags and run some processing and see when you were able to get triggers. So you can export that into Excel or MATLAB and do some analysis of when that glitch was occurring and see if it's periodic or aperiodic. And that's going to help you debug your system. You can also use, we have a color grade or an intensity feature on the 6000X, and you can actually scroll through all your segments and build them up into this intensity waveform and look at all your segments overlapped on top of each other.
Okay. Well, at this point, we're going to have to wrap up. We do have time for one more question, and that is, how can I filter high frequencies when I measure a slow signal?
Sure. So our scopes, the Infinivision scopes, all the Keysight scopes, in fact, have some built-in bandwidth features, bandwidth limiting features, so you can turn on filters at 20 megahertz or 200 megahertz or a gig. So depending on what frequency levels you want to filter out, you can turn on those bandwidth filters. In the Infiniium series of oscilloscopes, you can set a custom bandwidth filter to be any frequency you want. If you want to do it less, maybe a little not quite as clean, you could also just use a lower frequency probe and look at the frequency response of the probe and use the probe itself as a bandwidth filter. But we usually recommend using those built-in internal bandwidth filters for the scope.
Okay.
Good question.
Well, that concludes today's presentation.